We have learned from Kevin Planck's statement that we can never have a heat engine with 100% efficiency. Then, what is the maximum efficiency of a heat engine? A French engineer named Sadi Carnot tried to calculate this maximum efficiency of a heat engine. As a result, he discovered a special thermodynamics cycle, which he named after himself, Carnot cycle. He discovered that in order to have maximum efficiency, a heat engine needs to have 4 processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. You might be thinking, why did he choose these 4 processes? Why not any other process? Sadi Carnot knew that if he wanted to have maximum efficiency, he would need to remove all the inefficiencies and losses that happen in a normal engine that cause increase in entropy. So he needed to make a cycle where the entropy change was 0. Let's look at a heat engine. The condition we have is that entropy change for the cycle is 0. Here there are 3 main processes: heat addition, work extraction, and heat rejection. Heat addition happens between the hot reservoir and the engine, and heat rejection happens between the engine and cold reservoir. We can use the equation delta S equal to Q by T to calculate the individual entropy changes. Here, heat QH is lost from the hot reservoir at temperature TH and absorbed by the engine at some temperature T1. Similarly, heat QC is absorbed by the cold reservoir at temperature TC and lost by the engine at some temperature T2. The work extraction happens without any heat transfer, so it can be removed. So this becomes our new condition for the perfect engine. The only way for this to happen is if T1 is equal to TH and T2 is equal to TC. Hence, in the ideal engine, heat is added at a temperature of TH and is rejected at a temperature of TC. If the temperature on both sides is the same, that makes it an isothermal process. So the processes are isothermal heat addition or expansion and isothermal heat rejection or compression. Now we need a way to transition between these 2 temperatures without generating any entropy. No entropy means no heat transfer, which is also called an adiabatic process. So we have 2 new processes: adiabatic expansion, to decrease the temperature to TC, and adiabatic compression, to increase the temperature back to TH, so that the engine can function continuously. So in total, we have 4 processes: isothermal expansion from 1 to 2, adiabatic expansion from 2 to 3, isothermal compression from 3 to 4, and adiabatic compression from 4 to 1. The efficiency of such a cycle can be calculated as desired output by the input given. Here, the desired output is the net work done, and the input is the heat from the hot reservoir, QH. But the net work done is the sum of the work done in each individual process. So we need to calculate the work done in each individual process and add them together. Process 1 to 2 is isothermal expansion, so the equation is PV is equal to constant. Using this relation, in the equation for work done, we get work done from 1 to 2 as constant into log V, from V1 to V2. Or, is equal to constant into log V2 by V1. We know from ideal gas law, that PV is equal to Mr specific T. But PV is equal to constant, and so we can substitute Mr specific T, or Mr specific T1, as the constant in the earlier equation. Which gives us work done from 1 to 2 as Mr specific T1 into log V2 by V1. Process 2 to 3 is adiabatic expansion, so the equation is PV raised to gamma is equal to constant. Using this relation, in the equation for work done, we get work done from 2 to 3 as constant into V raised to 1 minus gamma by 1 minus gamma from V2 to V3. Or, is equal to constant by 1 minus gamma into V3 raised to 1 minus gamma minus V2 raised to 1 minus gamma. We know that PV raised to gamma is equal to constant at both points 2 and 3. And so, we can substitute this in the earlier equation, which gives us 1 by 1 minus gamma into P3 V3 minus P2 V2. Using the ideal gas law, we can rewrite the PV terms as Mr specific T3 and Mr specific T2. And so the work done in process 2 to 3 is Mr specific by 1 minus gamma into T3 minus T2. Process 3 to 4 is isothermal compression, so the equation is PV is equal to constant. Using this relation, in the equation for work done, we get work done from 3 to 4, as constant into log V, from V3 to V4. Or, is equal to constant into log V4 by V3. We know from ideal gas law, that PV is equal to MR specific T. But PV is equal to constant, and so we can substitute MR specific T, or MR specific T3, as the constant in the earlier equation. Which gives us work done from 3 to 4 as MR specific T3 into log V4 by V3. Process 4 to 1 is adiabatic compression, so the equation is PV raised to gamma is equal to constant. Using this relation, in the equation for work done, we get work done from 4 to 1 as constant into V raised to 1 minus gamma by 1 minus gamma from V4 to V1. Or, is equal to constant by 1 minus gamma into V1 raised to 1 minus gamma, minus V4 raised to 1 minus gamma. We know that PV raised to gamma is equal to constant, at both points 4 and 1. And so, we can substitute this in the earlier equation, which gives us 1 by 1 minus gamma, into P1 V1 minus P4 V4. Using the ideal gas law, we can rewrite the PV terms as MR specific T1, and MR specific T4. And so the work done in process 4 to 1, is MR specific by 1 minus gamma, into T1 minus T4. Adding all these together, we can take the T terms common. Since process 1 to 2 and 3 to 4 are isothermal, T1 and T2 are both TH, and T3 T4 are both TC. So we can cancel these 4 terms, and the last term can be removed. We can use this expression in the equation for efficiency. But from the first law, delta U is equal to Q minus W for process 1 to 2. Since process 1 to 2 is isothermal, there is no temperature change, and hence the internal energy also does not change. So the heat transfer in process 1 to 2, which is same as QH, is equal to the work done from 1 to 2. Substituting this, and using the value of W12 that we derived earlier, we can cancel out all the MR specific terms, giving us 1 plus T3 log V4 by V3, by T1 log V2 by V1. But process 2 to 3 and 4 to 1 are adiabatic, and so, PV raised to gamma is constant in those processes. Combining this with the ideal gas law, by using the value of P, we get the form, MR specific T into V power gamma minus 1, is equal to constant. Since MR specific is also a constant, for a given gas, we can group it with the constant in the RHS, which gives us TV raised to gamma minus 1, is equal to constant. We can use this relation for process 2 to 3 and 4 to 1, and rearrange. Here, T1 and T2 are the same as TH, and similarly, T3 T4 are the same as TC. By taking the reciprocal, we can equate the two, which gives us V3 by V4, is equal to V2 by V1. Substituting this in the equation for efficiency, we get 1 plus T3 log V4 by V3, by T1 log V3 by V4. Since the log terms are just a reciprocal of one another, its value is negative of the reciprocal, and so they cancel out, leaving only the negative sign. And so the efficiency of a Carnot cycle is 1 minus T3 by T1, or 1 minus Tc by Th. This derivation is very lengthy. So, there is no need to learn it by heart. But, if we understand how each of the terms were derived, then we can solve any questions related to the Carnot cycle.